My name is Jarrod Vaillancourt. I'm with Applied Nanofemto Technologies. I just want to say thank you for inviting us here today to talk about our work we've done on some imaging arrays. So who we are, we're Applied Nanofemto Technologies. We've been around since 2005. A very small company based out of Lowell, Massachusetts. Currently there's just 3 of us working there. And where we are is we're funded through SBIR, STTR funding from the government at the current time. Small Business LLC. So really what I'm going to talk about is some of the current work we're doing with NASA, which is based on trying to develop a compact hyperspectral imaging array. It's really two innovations in one. The first one here, the bottom bullet, is a quantum dot photodetector material that we grow ourselves. It's based on indium arsenide quantum dots, and what we can do is, by varying the material parameters that we're growing, we can start to image in both mid-wave and long-wave infrared wavelengths. The second innovation is really a plasmonic filter that we're developing to do the hyperspectral filtering. So we're kind of growing a broadband detector material and integrating that on top of it a hyperspectral filter. So that's how we're getting the filtering capability. So looking forward at if we're successful developing this, what can we get? And these are all estimates based on the frame rates that we have, the imaging array size, the distance that we're viewing. So some of the, what we estimate to be able to do is getting a spectral and spatial resolution of both 1 inverse centimeter and about 1,250 lines per inch of resolution. Sensitivity, we estimate that if we're successful in developing this, we can try to sense 10 parts per billion chemicals, that's leading to the high sensitivity. And this is a 2-dimensional array, so it's a staring mode imager. So it is based on a photodetector technology which can image at very high frame rates for high-speed detection, but it's not required. If you're looking at very cold, very dim stars, you can actually slow the frame rates down, integrate for longer, and get more photons in. So it's not required to be high speed, but it can. Due to the fact that we can actually get many hyperspectral cubes per second, you can actually start to have very high speed detection rates, low false alarming. And because everything is integrated onto the focal plane array. So once we make our focal plane array, you may or may not be familiar with it, but it's really going to be about the size of a silver dollar, this chip. And then that's our mid-wave and our long-wave imager. It can operate in both depending on bias tuning. And then to make this hyperspectral, we're actually not going to really be adding any appreciable weight or size or moving parts. So it's really going to be the same chip. You won't see the difference when we're done. And I'm going to go into more detail because it doesn't sound like something that can be done, but when you see what I'm talking about, you'll understand that this is a very good for low-cost, small-size applications. Currently, we are around, we would estimate a TRL3. We have a lab prototype, something benchtop stuff that we've really used to prove the concept. In a couple of years, we'd like to be up to 6 to 7 if we can be successful. So the uniqueness of our innovation is, as I said, we're going to be able to add hyperspectral sensing to this without really increasing the weight of the sensor, the size of the sensor. We're not going to decrease reliability. We're not going to put any other power requirements that we need to do this. This is a passive method that can be integrated during the fabrication of your sensor. And that's going to what leads to the very low cost, very high reliability. The strong plasmonic enhancement. I have some slides in the future, in the next few slides, that really go over what the plasmonic enhancement is and why we say it's a filter, but it's not acting as a traditional filter where everybody in the audience might think it is. I'll go through it. And the next thing is the high operating temperature detector material. Most infrared detectors and 2-dimensional imaging arrays require very low cooling, cryogenic cooling, to operate and to get high performance. For our single pixel detectors, the larger area stuff, we can operate near room temperature. And currently we're trying to push that to large format imaging arrays. That's work that's ongoing. And if we're able to do that, we will be able to really provide low-cost a low-cost alternative for small satellite applications. So that's kind of the overview, quick overview. I'm going to go into more detail of what we're doing, and this is how it could be used. Many of you may be familiar with this, but this is the Afternoon Constellation. It's a mission that's been going on for roughly a decade, where they're launching several satellites. Some have gone in and out of commission during this time. But what they're doing is it's an Earth-absorbing mission where they're monitoring the trace gases, temperature, mineral identification, and it's just in synchronous orbit with the Earth, and they're continually monitoring it. And the reason I find this the most interesting is you can see the instrument they're using, the last close to the bottom, are 3 high-resolution grating-based spectrometers. So where they're filtering the light using a grating. So you have a grating that you have to fabricate and integrate with your detectors, and now it's going to move through and it's going to scan. And this does this very well, very high resolution. And what we're doing, I'm not saying is a replacement for that, but what we're doing is trying to give this capability in something you can hold in your hand. Whereas with these spectrometers, it's 131 kilograms or so per spectrometer. These are too large for small satellite or potentially a CubeSat sort of an application. Another mission that they're working on is the WISE mission. And this is actually one of the really good applications for our technology. So they're looking at very dim, very dark objects. So here you have the satellite, which is really just an imaging array, along with all the support electronics in the lenses they need, and it's made up by 4 megapixel arrays. Each array has a specific wavelength it's looking at: 3.6, 4.2 microns, 12 microns, and 22 microns. Now, as I said, our hyperspectral filtering technology, which is calling a filter, is actually an enhancement technology. So we can design a hyperspectral filter that isn't going to filter out the wavelengths that you don't want. What it does is you choose the waveband you want, and it's going to enhance that 10 to 18 times. So just that technology on something like this would actually give you a stronger signal coming in. And it's passive. It doesn't require extra cooling. So I'm going to go into a little bit more detail now. So this is kind of what we envision, if we're successful, what this will look like. It's simply a megapixel array. We're shooting for a large format array. We've demonstrated from smaller formats into a small box, roughly 0.3 by 0.2 by 0.1 meters, something that's a kilogram or less. This is really getting into the point where you could hold this hyperspectral sensor in your hand. And again, we'll just reiterate the resolution, the spectral and spatial resolution, and the high sensitivity that we hope to attain. So you can see really this consists of just, we have this 1K by 1K two-dimensional pixel array. We have an imaging length and then your imaging system here. So there's no moving parts, which actually gives you really, really high reliability, which is something that is really attractive. Again, being so small, you can actually launch many of these at one time rather than just one large satellite. Okay, so here's going into a little bit more detail on this, what I've called a plasmonic filter. It's really plasmonic enhancement of your desired wavelength. And then the second technology that I'm going to go into is a high operating temperature quantum dot detector. So for some of you may or may not be familiar with this, but if you have a metal interface and a dielectric, and you're going to put some sort of a metal grating, there has to be a structure here of metal. If you can design it and satisfy these electromagnetic equations, so you have to choose a proper metal, the periodic structure in the metal has to be proper, and it has to be all the right sizes. What you can do is begin to confine the electromagnetic radiation here at the surface, at the interface, or just below it. And here's an image that we got that kind of shows it visually, what you're doing. So you're taking the desired wavelength that you've designed your structure for, and as it comes into your detector material, it's going to be confined there. So you're going to get an increased absorption for the desired wavelength you want. And this kind of does sound too good to be true. I think some people in the audience look at me and say, I'm going to have a hyperspectral filter that's going to give you actually better performance. It's going to have no power requirements. It's not going to add any weight. It doesn't have any moving parts. And people kind of who aren't too familiar with this say that's all too good to be true. But these are 3 technologies that have been proven and that continue to go out there to improve research based on this physics. The first is the surface enhanced Raman scattering. They're using surface plasmonic resonance to increase absorption in thin film solar cells. And here you're doing super resolution imaging by using subwavelength focusing. So this is just kind of, the technology does work. And what we're going to do is apply this to detectors and imagers. So next slide. So the first proof of this concept is to take a photodetector that we've made with our quantum dot material. Here in the top image, you can see the edge of the mesa here. This is a 250 micron circular detector. You have a bottom contact on the top bottom of the mesa. Here's our top metal electrode. So you have your top bottom contacts. And inside here is our plasmonic resonance structure. It's simply a perforated metal film at this point, where the dimensions have been optimized for just beyond 8 microns. So this blue trace down below is actually the reference detector with no plasmonic enhancement. And then this pink trace, you can see the enhancement here where we're getting very high enhancement just at the desired wavelength. So that's where the filtering comes in. We're terming it a filter, but it's not as you would initially think, where I'm just attenuating certain wavelengths and I'm allowing most of the wavelengths I want to pass through. And this is something that's very attractive because, like I said, you're actually getting enhancement, extraordinary transmission, more than 100%. And it's at your desired wavelength. It can be integrated exactly, monolithically with your photodetector, so that's where the no moving parts comes from. Next slide. So that was a large area detector. Next, it's a whole different device to go to a two-dimensional imaging array. The pixel size is much smaller. Can this still work? Well, we did some simulations is how do we integrate this in? Before, you could see on the top of the pixel, we put the plasmonic structure. And we had the light coming from the top of the pixel through it into the active material. Well, in a focal plane array, you have to flip your pixels upside down to mate it with your integrating circuit. So how does that work? After I've done all the work of growing this material, fabricating it into the array, hybridizing it with my silicon readout electronics, then I have to underfill it with epoxy. Then I have to mechanically lap off the substrate because you can't have all that substrate material there that's just not useful. It'll crack when you cool this. And then I have to go through and do a selective etch so I can actually remove all of the substrate. Well, do I want to do another round of photolithography and fabrication on this very expensive chip that maybe have taken a couple weeks of work? You don't. So what we've proposed and we simulated here is, well, let's put the plasmonic structure still on the top of the pixel. So right in here, we've etched a mesa. We put our plasmonic structure over it. We passivate it. We have the indium bump that you need for your hybridization. As you flip this around now, so if this is the top surface of the pixel, we have incident light here. This is a CST simulation of what will happen. Here's our plasmonic structure, and here's the hole that we've perforated in the middle film structure. You can see that it will provide the enhancement right here in the active region. But what happens if we flip this? We have the same plasmonic structure, but now we launch the light from the backside. So we get an absorption here. It interacts with the plasmonic structure, is enhanced, and goes back in. You can see that right here is where our active region of our quantum dots will be. We're actually going to get much better performance, and this is what we've seen. So the first data that we saw, I showed around that 8 micron peak here, backside illuminated, what we're calling a backside illumination. You can see that we have more than 18 times enhanced signal at our desired wavelength. So this is where the filtering is. This is why it's no power. This is a passive film that I'm engineering and I'm applying to this. So it actually is even more compatible with focal plane arrays than it is with large area detectors, which is something that we didn't quite expect, but we found this simulation and we experimentally verified it. Next slide. So we believe that this will work, so we went ahead and fabricated a small area array. This is an image taken with a 320 by 256 imaging array, compatible with a commercially available readout. Here are all the pixels. They're on a 30 micron pitch and a 28 micron pixel size. Here's our plasmonic structure that we have surrounding the pixels. In the center is our ohmic contact, on top of which we put an indium bump. And this little pictorial kind of represents everything. So here, this is the substrate that gets removed down. And here's the imaging with it. During the fabrication of this array, there was a problem with the liftoff where all these pixels here do not have the 2D Hall array. They only have the ohmic contact and indium bumps. Everything surrounding it does. And you can see in the image the higher intensity that the plasmonic enhanced structure will give you. So this is why it's a filter, an enhanced structure. So that's really good, and this is really compatible, and we're excited to move this forward to larger arrays. Like I said, this is still a small area. So now up until this point, that last device was a single wavelength. So we optimized it just for a long wave, one wavelength. How do we move this into what we would call a hyperspectral filter? Here, this is more simulation data of the transmission through a filter through several different filters. So you can see here we're showing what the transmissions would be for 10 different wavelengths. And this is why we're claiming hyperspectral capability. This is something that we have experimentally verified, where we can start to tune the wavelength. We pick a wavelength we want, we can design the structure to it, as long as we know, the metals we want to use, what is the detector material. And it's not required that we use our quantum dot detector material. As long as we know how the electromagnetic waves will interact with the material, we can design the proper plasmonic structure. The structure for one material is not going to be the same as the other, but we can tune it. And as I said, we have next slide. You can just go through them. We verified this on large area detectors. We've yet to make an imaging array of all this whole plasmonic filtering stuff. And like I said, it can be fabricated on any detector material, so it could be optimized for quantum dots or some other commercially available product. There's no misalignment. There's no calibrations that are going to be needed. Once you fabricate this, you're set, and it's not going to change. Next slide, please. So that was our plasmonic filter technology. To talk about the quantum dot enhancement, the hot quantum dot detectors. The image here shows an AFM image of the materials here. These are indium arsenide quantum dots. Our last speaker spoke, it was a little bit, and he had a couple questions about the lattice mismatching. Well, here, he avoided it, and they took great pains to do that because it's required. But here we actually kind of take advantage of a lattice mismatch. We intentionally lattice mismatch our materials. And once we do that and we can grow the proper thickness of the material, we can start to form these quantum dots. Each of these white dots is just a cluster of indium arsenide atoms. And by doing that, it provides true three-dimensional quantum confinement. This is really a very interesting application of quantum mechanics. It was Richard Feynman who really said, if we can really exploit this, we can start to tailor materials to what we want. Well, indium arsenide shouldn't be absorbing in mid-wave and long wave, but if we can start to make these quantum dots, we can make it do that for us. And what's nice about this versus some of the other technologies is this is normal incidence sensitive. Some other quantum, depending on the quantum selection rule, some other materials won't really absorb if your light comes in normal to your surface. This will have that absorption. You don't have to have any diffraction gratings or anything. It's also nice that it is based on some mature technologies. These can all be grown on large area substrates. The fabrication can be done with industry standard tools. There's no real special steps that are taken to make this into an array. And we have operated these devices at as high as 230 Kelvin. So that's very good for mid and long wave. The pictorial here of how this works is these rely on inter-subband transitions rather than a band-to-band in a traditional semiconductor. So everything happens here in the conduction band. So as this well here is actually a quantum dot. And if you can make this sufficiently small, you get two energy levels that you'll confine within this potential. The first is the ground state. This is where your electrons will stay. This is where they want to be until the light comes in, and it'll absorb the energy from the light and raise to the higher level. And if you're biasing this, you get the band bending so that this electron will now be collected as photocurrent. That's the basic principle of what we're doing. Next slide. Here are a couple of spectras that we've taken with some of our detectors, both covering the mid-wave and the long wave. We have pushed this out to past 11 micron detection for the peak wavelength. So this can really be tuned by the growth structure. We can actually go a little shorter, a little longer. There is some tunable, and that's what's nice about exploiting these quantum mechanics. And this is the same detector. So another benefit to this is you don't have to design only a mid-wave detector. You don't have to design only a long-wave detector. What you can do is you can design a mid-wave band and a long-wave band and then vertically integrate them. And then as you want to detect which spectrum, it would either be by applying a separate a bias, maybe a positive bias that will actually have a stronger mid-wave absorption, or a low negative bias will have mid-wave, so you'll preferentially absorb the mid-wave. As you go to a very large negative bias, you absorb the long wave. So you can actually start to do vertical integration of a multi-band detector, of which you can put a plasmonic filter on top of it. Next slide. You can just go through them. So this first pictorial demonstrates that. We took that material where we stacked these two bands, a mid-wave and a long-wave band, into one pixel and created a small imaging array. So under a low positive bias or any under low bias conditions, this mid-wave, which has a higher energy transition, because we've tailored the wells around this quantum dot to give it this. So the mid-wave light, which is higher energy, will excite this electron up to this level. Under the low bias condition, there's a small barrier here, and it can tunnel through it. This long wave, there's actually a larger barrier here. The probability of tunneling through this barrier is very low. You will collect a few long wave photons under low bias condition. You can't turn that off. You can't make that zero. But you can actually start to get this image. So the top image here is collected with a mid-wave lens, so in the 3 to 5 band. And you can see the same image with the long wave lens. This person is much dimmer. You're getting much fewer photons. The next case is, this is the same device. All we did is change the bias that we're operating this pixel at. As we go to a larger bias here, and this is taken with the mid-wave lens, the 3 to 5, he's very dim because you're not having as many mid-wave photons here. Under the large bias with the long wave, the 8 to 12 micron lens, you can see he becomes very bright. So you're getting many more photons. Next slide. And here's just some of the data that we have. We're up 10 to the 7 D star conditions at 230 Kelvin. And you can see we're getting mostly mid-wave operation here at this time. 77K, you get a much wider band of operation. This is just some background. Okay. So here's the slide that I want to use to really introduce our idea here. Here I'm showing this, and this could be in any number of wavelengths here, but I'm showing a 16 wavelength configuration. So if I were to take a 1K by 1K focal plane array and break this into 16 bands. So each pixel of this 16 band will have a plasmonic filter tailored for the specific wavelength I wish to have. And you can choose any wavelength you want as long as your detector material is going to absorb at that wavelength. So anything in the mid to long was what I've shown. And it can be any wavelength, any number of wavelengths, any combination of wavelengths within that band. And they don't have to follow any specific order. You can actually take off one of these filters and just have regular, if you needed a background signal in your picture, you could just have one without a plasmonic filter in here. So this is kind of the idea. Within the 16 band image, if we were to do a 1K by 1K, it gives you a resolution of 256 by 256 image for each. And at this point, it just becomes dependent upon how you do the image processing after you've collected the image. So next slide. So just to sum up, we have pixel integrated narrowband plasmonic filter. Again, it's not the filter in the traditional sense. This is actually an enhancement technique, so you can enhance the desired wavelength. Something that's really a powerful technique for imaging very cold objects. You automatically get an increase in the number of in the responsivity of your device. And then you can operate these at a higher operating temperature, something that becomes really attractive as you try to go to small satellites. You want to start to eliminate all the cryogenic cooling. And it should be very low cost because you don't need the high cryogenic cooler. It's based on 3-5 materials that are very well known and can be grown and processed efficiently. So we'd like to thank NASA for the funding. We're working on a phase 2 now, which is actually working on, we didn't put it in here, but it just wasn't time to go through a photonic antenna for chemical detection, but we're in the middle of this one. And we just finished up our phase 1 work on this hyperspectral imaging. We also, have branched out to other people. Being 3 people, we can't do all the work. So Lockheed Martin is very excited about this, and if we can give them an array to look at, they're willing to put it in one of their UAVs and help us do some of the testing on a real actual platform, which is something we really appreciate. And again, we work very closely with UMass Lowell for our STTR work, and we have actually done some exclusive licensing of some of the technology, along with patenting some of our own technologies. Okay. So what we've demonstrated here, we actually demonstrated it as a single pixel detector, imaging arrays, high operating temperature, and we started to put all these pieces together to really prove the power of this. And we've achieved the hyperspectral imaging on a benchtop test system with the larger imaging arrays, with the larger pixels. The next step is we're really looking forward to pushing this to a large format imager that can do the hyperspectral imaging is really where we want to see this go. And then it would be really, really exciting to get this up onto a UAV platform and do some actual real world testing. To do that over the next 2 years, we estimate it would cost about $1.5 million to do that. And it would take about 2 years. So why should this be invested in? It's an enabling next generation technology. It's really something that we're really pushing forward, and you can do a lot with it. It's not the end all. It's not going to replace a gradient-based spectrometer. Those are very good at what they do, but you're not really going to make a high resolution gradient-based spectrometer on a CubeSat. This is something that potentially could do that if it's successful. Another thing to hear, the WISE mission, they're imaging for about 1.1 seconds. Well, our technology can actually go much faster and be much more reliable because there's no moving parts. You don't have to worry about, okay, I've sent a satellite out, it's traveled for years, and it just failed the calibration. What do I do? Something's not moving correctly. No, there's no moving parts. This is very small. It's really just the sensor, the lens, and your sat. So, and again, this plasmonic filter, we call it filter, but it's really enhancement, is really excellent for very, very cold objects, something that's not going to emit a whole lot of flux. Highly reliable, and we can really hope to push this down to cost where this can be used quite extensively. It has a lot of applications for NASA-based, whether it's Earth sensing or heliophysics. It has many things in industrial, DoD applications, commercial applications. So this is who I am. Please feel free to talk to myself at any time. I'll be around. And then a little bit about the company, and then I'll take questions. So we are very small, but we actually have the capabilities of a large company. It's something I'm very proud of. We have our own MB system that we operate continually to grow our own material. We do all of our own fabrication, all of our own hybridization and testing. So we're very small, but we can really turn things around quickly, and we're very cost effective in our work. Just switch up. So this is the last slide. This is who we are. This is our system. Can grow up to 3-inch material, which we're adding some new capability now for some antimony growth. We work in state-of-the-art clean rooms, and we have a full test suite for both detectors and imaging arrays. So I'd like to take any questions now. The simulation data, you mean? Within one pixel? The peaks I showed were actually the transmission, so that's the enhancement of your band. So you're really only going to enhance one wavelength at a time. You can't do multiples.
What's the limitation of going below 3 microns?
I'm sorry?
What are the limitations to keep you from going below 1 micron, 3 microns? You're showing are falling off then.
It's really limited by just choosing the proper metal and engineering the right structure. The shorter the wavelength, the smaller the structures you're needing, so you may need to go to a more advanced technology. A lot of the long wave can be made with just simple contact lithography. To go 3 microns or below, you're probably looking at advanced, deep UV steppers or E-beam. But it's really a fabrication question. Yes.
Yeah, nice talk. Beautiful. You are raising the temperature, the detection temperature on these. So I didn't really catch that. Was that just because of the plasmonic resonance bringing in more signal?
It's actually both. That is one of the factors. The data that I showed you at 230 Kelvin actually has no plasmonic structure. That's some older data. That's due to engineering the MBE growth. So quantum dots have a very low density of state, so it has an intrinsically low dark current. And if you can provide the right layers surrounding the quantum dots, and you can grow defect-free. The quantum dots are defects, but if you can keep them all at a uniform size and not have any very large quantum dots, that's another key to getting low dark current and high operating temperature.
So at one point you said you could enhance the transmission greater than 100%. That seems to violate conservation of energy. So I'm wondering what you meant by that.
Yeah, no, that was work that was done by T.W. Ebsen. So what you're doing, let me go back, is you're actually starting to take all that light and just focus it. The analogous to a lens where you're focusing on a point, but you're not really putting it down there. So you can actually start getting very high. So this wavelength before this, you can get responsivity above 1 because you're putting all that light into a very small region. It's work done, you know. It was actually, Ebsen was the first person who started this many years ago. Okay, thank you very much.